So let us start with the front module, where I really give a short crash course on deep learning. Not a full-fledged course, but really just the basics, what we need to understand deep learning over structured data, the things we're going to see later. So we'll first understand the conceptual abstraction, the general idea of deep learning networks, how they're structured and what is the mathematical formulation. Then we're going to look at specific building blocks and architectures with a focus on what we'll encounter later in the course, in the next modules, okay? And specifically the attention mechanism. We're going to give a lot of emphasis to that. Then we're going to look at the lower level aspects of learning deep learning networks, specifically backprop or backward propagation and GPU computation and how you connect to the GPU through languages like CUDA. And this is not because we need or expect you to program at that low level, but I want you to understand what your programs compile to. What is the context? What is the requirement? What happens under the hood? And then what are the practical limitations that we meet when we are building a deep learning network or architecture over structured data? Okay, so again, not a full course on deep learning, the basis, and the focus is what we'll need in this course for deep learning over structured data, tables, graphs, databases. So this module has three parts. First, general abstraction of deep learning networks, then some popular neural networks, feed-forward, MLP, and then the attention. Okay, and the third part is going to talk about learning aspects, backward propagation, dropout, and GPUs through CUDA. Okay, so we'll start with the first part, and specifically, let me give some very basic notation quickly. So a vector is a column vector. We write it like this. Okay, a column of values, V, n-dimensional vector. I can also write it as the row vector transpose, okay? And when there's no risk of a confusion, I write the column vector as a row with ordinary parentheses, rounded parentheses. Okay, this is confusing, but I'll use it when there is no risk of confusion. Okay, some more notation. So the spaces of elements, we've been using it already, but just to put things in order, Rn is the space of column vectors with n elements. Rn times n is the space of matrices, each having n rows and m columns, okay? So you can really view a vector as a matrix of n rows and one column. Okay, Rn can be identified with Rn times 1. Okay, now just the law of transpose over product. So if you have a matrix A and a vector V, then AV is a column vector, right? And then the transpose is a row vector. This is the same as taking the transpose of V and multiplying it by the transpose of A. Okay? And in general, it's very useful to remember that AB transpose is the same as B transpose multiplied by A transpose. Okay? So we switch. Now, I'm also going to use this notation of element-wise product. So I have two vectors of the same length n, v and u, and v circle dot u is the vector of n elements, where the ith element is the product of the corresponding ith elements of the two vectors, vi times ui. Okay? So now we have two notions of product. We have the usual dot product, v times u gives you a scalar, a number, okay? And we have the element-wise product, the circle dot u, which is a vector of length n. Okay, and we're going to use that. And that's all. With that, we can start talking about the abstraction of deep learning, deep neural networks.